But we know that protons and neutrons are actually made of quarks. A proton has two up quarks and a down quark, and a neutron has two down quarks and an up quark. So now we can actually make the Feynman diagram more detailed. We can say that a proton coming in consists actually of three quarks, two up quarks and one down quark. Two of those quarks will go out unchanged, one of the up quarks and one of the down quarks. But this up quark is changed into a down quark by the emission of a W plus boson, which then decays into a positron and a neutrino. So what we've actually learned is that the W plus and the W minus bosons convert up quarks into down quarks with the emission of a W plus boson, or down quarks into up quarks with the emission of a W minus boson. In the Standard Model there are 6 types of quarks, and the W plus and W minus bosons are responsible for changing not only up to down, but also charm to strange and top to bottom. But there's a puzzle here. W plus and W minus bosons are relatively heavy at about 80 GeV. We measure mass in terms of energy because we simply use the formula E equals mc squared, and if you take the mass of a particle in kilograms and multiply that by c squared, the speed of light squared, you get an energy term. Strictly, I suppose we ought to say that the mass is GeV divided by c squared, but physicists frequently leave the c squared off. So a W plus and W minus bosons weigh or have a mass of about 80 GeV. By contrast, the protons and the neutrons each have a mass of just less than 1 GeV. So how can it be that a proton can convert into a neutron by the emission of a particle that is 80 times heavier than it is? Where did the mass come from? For this we have to go back to Heisenberg's uncertainty principle, which you may recall is written like this, that the uncertainty in position multiplied by the uncertainty in momentum must be greater than h bar over 2. There is another version of the Heisenberg uncertainty principle which says that the uncertainty in energy multiplied by the uncertainty in time must be greater than h bar over 2. This doesn't quite mean what it looks like. It seems to imply that you can have any amount of uncertainty in energy and any amount of uncertainty in time, provided their product is greater than Planck's constant. But in fact it means quite the opposite. What it means is that you can have an uncertainty in energy for a very limited time, and that the more energy you have, the less time you can have it for. It's almost like you're borrowing energy from nothing, provided that you pay it back very, very quickly. And that's precisely what happens here, that a W plus or a W minus boson borrow energy as it were from nothing, but they have to pay it back very, very quickly, and that's why a W plus and a W minus boson lasts for only about 10 to the minus 25 seconds before all that energy has to be paid back. And what is released is, of course, the relatively small positron and neutrino. We can now move on to look and see what is happening within the protons and the neutrons. And this is where we come into the world of quantum chromodynamics. We know that protons and neutrons each consist of 3 quarks. The proton has 2 up quarks and a down quark. The neutron has 2 down quarks and an up quark. But we remember a principle called the Pauli exclusion principle. This is usually referring to electrons in atoms, and it basically says that no 2 electrons can be in the same quantum state. And that's generally regarded as being a principle which applies not only to electrons, but to all fermions, that is, all particles, including quarks. The only group that this principle doesn't apply to is the bosons. So you would expect that quarks also are forbidden to be in the same state. But within the proton, it appears that they are. So the three quarks in a proton or neutron must be in different states, otherwise they would breach the Pauli exclusion principle. There must therefore be something that distinguishes one quark from another and puts it into a different state. And physicists have given that the name colour. Each quark in the proton or the neutron must have a different colour, and the colours which are conventionally used are red, green and blue. Now let me make it clear. The quarks are not painted red, green and blue. This really has nothing whatsoever to do with colour. The word colour is simply used as a means to distinguish one quark from another. So we say one is a red quark, one is a green quark, and one is a blue quark. But I repeat, it has absolutely nothing to do with colour at all. But because we use the concept of colour to make the distinction, that is where the word chromo, which means colour, comes from in quantum chromodynamics. Now we have learnt that the up quark and the down quark can interchange by the emission of a W plus or W minus boson. Can red quarks change into green or blue quarks? Well, yes they can, and that process is governed by the bosons called the gluons.